Hi, my name is Matt Hoffman. I'm going to be talking to you today about round-off error and its effects in Metropolis-Hastings Accept-Reject Steps. So, if you take nothing else away from this presentation, the thing you should take away is that if you're not careful, Metropolis-Hastings might reject a lot if you use low-precision arithmetic, especially if you have a lot of data. So to illustrate this, on the left, this is the acceptance probability of a Hamiltonian Monte Carlo Metropolis-Hastings algorithm on some synthetic linear regression problems with different amounts of data as a function of iteration number. And you can see the acceptance probability is essentially 1 if we do it in float 64. If we drop down to float 32, the situation becomes much worse, especially as the size of the data set increases. So I'll spend the rest of the time trying to give you some intuitions for why this happens and what we can do about it. So the Metropolis-Hastings algorithm is a meta-algorithm that underlies essentially all Markov chain Monte Carlo or MCMC methods, with the possible exception of Gibbs sampling. Things like Langevin dynamics, Hamiltonian Monte Carlo, random Metropolis, etc. Metropolis-Hastings is really a meta-algorithm. It takes a target distribution, P of theta. This could be like P of theta given x if we're trying to do Bayesian inference, and a proposal distribution, which is what distinguishes different Metropolis-Hastings algorithms, which I'll call Q of theta prime given theta. Right, so the way the algorithm proceeds is each step we sample a proposal theta prime from Q of theta prime given theta and accept it with this probability alpha, which is the minimum of 1, because it has to be a probability, of course, and this ratio P of theta prime over P of theta times Q of theta given theta prime divided by Q of theta prime given theta. Right, so this accept-reject step ensures that the stationary distribution of this procedure is in fact P of theta, and so this gives us a way of actually generating samples from the distribution we're interested in, if we do it long enough. So there's this very significant trend in machine learning towards using ever lower precision arithmetic, right? And there's some advantages to this. It reduces your memory requirements. It lets you get quite a few more floating point operations per transistor. In this talk, I'll focus on good old single precision float 32, but these lower precision formats like float 16, B float 16, tensor float 32, all these things are becoming popular. And they do seem to work surprisingly well if you're doing stochastic gradient descent on deep neural networks. So, fine. But Metropolis-Hastings does, at least in principle, assume that we're doing exact arithmetic. So to what extent does it matter that we're not really using real numbers? So I'm going to talk to get at that question. First, I'm going to talk a little bit about what I mean by round-off error. So there's one type which I'll call simple truncation. I'm not going to spend a lot of time on it, but basically this is just a question of how many significant figures are there in a 32-bit float? The answer is about 6. So this means that we can't even really represent very large log densities. So here's a little example of a way in which that might be a problem. But I think the bigger issue is accumulations of catastrophic cancellations. So if we're doing Bayesian inference, often we're interested in this log joint P of theta and x, which up to a constant is the same as log P of theta given x. And often that's a sum of many terms, right? A log prior plus a sum of log density, log likelihoods for each of these xn's. Now, naively, summing these terms leads to each time we do an addition, there is a little round-off error, and those many little round-off errors wind up getting added together, and they can actually accumulate into much bigger round-off errors. And this seems to be a much bigger problem than simple truncation. So, for example, if we try computing 2 million Poisson log likelihoods for a variety of random different rate parameters in float 32, then if we do everything in float 32, then we get the error distribution on the left. Looks vaguely Gaussian. It's got a magnitude of around 1. Whereas if we do the sums in float 64 and then just truncate, then we get this much smaller amount of error that is much more well-behaved. So, now let's talk about round-off in Metropolis-Hastings algorithms. So, just a little terminology first. So, we'll call the inaccurate rounded off log density that we wind up computing log p hat. of theta, which is just the true density log p of theta plus an error epsilon of theta minus a log normalizer that makes it so that p hat is actually a distribution that's properly normalized. But it'll cancel out everywhere we look at it. Right, so this leads to this perturbed Metropolis-Hastings acceptance probability, which is actually the acceptance probability that we wind up computing and plugging into our Metropolis-Hastings algorithm. Right, it winds up just being, we plug this p hat into the standard Metropolis-Hastings ratio. So that means that if we're doing Metropolis-Hastings with limited precision, if essentially what we're doing is actually sampling from, or rather at least we're leaving this perturbed distribution p hat invariant. So how is p hat different from p, the thing we actually want to sample from? Well, the first thing we might worry about is bias, right? So p hat, the way in which it's different, right, is it assigns higher probability to states with larger round-off errors, epsilon. Now, we might worry that expectations under p hat might be different from expectations under p, but they'll probably be pretty similar, and this is a pretty hand-wavy statement, but they'll probably be pretty similar to the expectations under p if, first, h, the function whose expectation we're interested in, is relatively smooth, and second, this error function, this round-off error function, epsilon of theta, doesn't have a lot of low-frequency components, right? So basically, if it's fluctuating around some constant value, basically because round-off error is driven by low-order bits, which should be fluctuating fairly quickly. As long as it's fluctuating kind of fast enough, then it probably shouldn't change our estimates of h too much. But that's maybe not an easy assumption to verify. But I would say that as big an issue is, does the algorithm even do an okay job of sampling from p hat, right? So there's this issue, right, that p hat assigns arbitrarily higher probability to states with larger round-off errors, but we don't have a way of preferentially proposing those states. We have to wait until we get lucky and get a large positive error. So intuitively, if epsilon has heavy tails or high variance, then basically once we sample a really big epsilon, we're stuck. We have to keep sampling until we get, just purely at random, another similarly extremely large round-off error. And so, for example, if the round-off error is normal under p hat, then that means that the error epsilon is log normally distributed, and that means that our acceptance rate, e to the epsilon is log normal, and that means that our acceptance rate goes down exponentially fast in the variance, and there's a derivation of that in the paper. So here's an empirical example coming back to that HMC on linear regression in a little bit more detail. So here, this is just a bunch of different synthetic data sets of different sizes. Step size chosen very conservatively so that the acceptance rate is extremely high in float 64. And as we might expect, in float 32, the round-off error does increase pretty much linearly with the number of examples because we're just adding more and more terms to that log density. And the acceptance rate does go down roughly as predicted by the derivation for the normal case in the paper as the variance of the round-off error goes up. Now, the purple and red dots are a little bit higher, the acceptance rates, than what's predicted, but I actually think that's just because we haven't actually converged to p hat yet, because the acceptance rates are so low that our mixing is terrible. So, what do we do? Well, first, how do we know that this is happening? Some warning signs that I've run into. One is just signs of round-off in the log density, right? So if you have these massive magnitude log densities, like minus 48 million, clearly you just don't have enough significant digits to the right of the decimal place to expect good things to happen. Another issue, another warning sign is that the acceptance rate doesn't go to 1 even if you decrease the step size, right? So a corollary is that if you do step size adaptation, trying to target some acceptance rate, those adaptation algorithms usually assume that if you drive the step size to 0, then your acceptance rate will go to 1. And if that assumption is violated, then the step size adaptation algorithm is just going to keep struggling to drive the step size low enough to get good acceptance rates. It never will, and so you'll wind up with a step size of 0. Finally, of course, the smoking gun is that if you can do things in float 64 and you see that they yield significantly higher acceptance rates, that's obviously very, compelling evidence. So how do we solve this problem? Well, of course, one option is to do everything in float 64, but that might not be palatable. For example, if you're running on a consumer-grade GPU. Another option is to compute all of the terms that are going into that big sum in float 32, but cast them to float 64 before summing so that you get rid of those catastrophic cancellations. Similarly, you can also stay in float 32 but use a compensated sum technique like Kahn summation. Another little trick is that you can write these log ratios as a sum of differences rather than a difference of sums, right? So you have a bunch of these y's whose log density you're computing. Take the difference between their likelihood under the proposal and the original state before you do the sum rather than after. And that actually makes those things zero mean and can help a lot. And then finally, hardware permitting, stochastic rounding could potentially be a solution in some cases. So, in summary, roundoff error can ruin a perfectly good Metropolis-Hastings algorithm. It is possible to get float 32 to work, but you do have to be careful. On the flip side, I would say that the big advantage of float 64 in this case is not so much that you have to do it, but it does make your life a little bit easier if you can afford it. Finally, watch out for these warning signs: big log densities, low acceptance rates, and this step size adaptation death spiral. Thanks a lot.